Okay everyone, welcome to AP Physics project. Today we'll be doing a question from AP Physics Unit 1 and Unit 2. Alright, so let's begin with our scenario. A ball is pressed against a horizontal spring-powered launcher, compressing the launcher from its relaxed length. The ball is then released and the rubber band-powered launcher launches the ball horizontally along the track that ends in a ramp as shown above. The ball has enough speed to leave the ramp and the ball reaches a maximum vertical height above the floor. K is the spring constant, x is the distance at which the launch is compressed, m is the mass, theta is the angle of the ramp, and h is the max height. So question number 1. The scenario is repeated with an additional rubber band added to the launcher, which means that we double the spring constant, okay? Indicate how h in this scenario compares to the h in the original scenario and explain why without using an equation or deriving an equation. Question B. Students derived an equation for h in the original scenario, h equals sine square theta kx square over 2mg, which might not be correct. Is this equation consistent with your answer for part A? Explain why or why not.
Answer to question number 1. Question 1a. So by increasing the spring constant, we increase the elastic potential energy as well. This means that when it is transferred into kinetic energy, it increases as well. If kinetic energy increases, that means that the velocity will also increase, resulting in greater height. Therefore, h in the second scenario is greater. For question 1b, the equation is consistent here as well, since the spring constant k will increase as the height h increase, assuming that everything else will remain constant. So on to our experiment. So we created a real-life model of the launcher and the ramp. We measured out some variables such as the spring constant, the mass, distance x, angle theta, and more. So here they are. The spring constant is 45 Newton meters. The mass of the ping pong ball is 2.7 grams. The compression distance x is 7 centimeters. The angle of the ramp is 35 degrees, and distance and height was later found during experimentation. As you can see in this video, we tested the ball launched from the launcher with 2 different sets. The first 3 times were tested with 1 rubber band, while the second 3 times were tested with 2 rubber bands. We then used a computer software to analyze the vertical height that the ping pong ball traveled. This can be seen in our comparison that when using 2 rubber bands, the ball go up higher with a mean of around 16 centimeters, whereas using 1 rubber band, the ball goes up around 10 centimeters. But there are some limitations to be noted, such as how slow motion footage makes a difference, how the angle that it was filmed from may be different, how the footage was not filmed parallel to the ground in some shots, and how some shot does not contain the full view of the projectile motion, which may hinder the program's ability to figure out some key variables.
Question number 2. The scenario is repeated with a different ramp with a larger theta. Question A. Indicate how h in this scenario compares to the h in the original scenario and explain why without using an equation or deriving an equation. Question 2b. Students derived an equation for h in the original scenario, h equals sine square theta kx square over 2mg, which might not be correct. Is this equation consistent with your answer for part A? Explain why or why not.
Okay, so now let's answer the question for number 2. So for part A, the answer is that the ball will go higher or that the h will increase. That is because the theta will increase. That means that the direction of the ramp is pointed upwards. When the ramp is closer to the y-axis, the ball's direction will go more to the y direction. Therefore, using the law of conservation of energy, the energy to travel the x distance will be used to travel the y distance instead, thus making the ball go higher but travel a less distance forward. For part B, the equation is consistent here as well, as the angle of the ramp theta will increase as the height h increase, assuming that everything else will remain constant. But we should also understand that we cannot always say that it is directly proportional, as sometimes the variable may be directly proportional to the square or to the root of some other variable. This shows that when we say that it is directly proportional to something, it may not actually be the case, since it could be directly proportional to the square root or to the square of something. In our second experiment, we can observe that by using two rubber bands, then changing the angle, the height increases as per our answer. There are some things to be noted. So in this experiment, we used two rubber bands, which means that the spring constant is 2K. We should also note that in both tests, the slow-mo camera is different, so the time will also be different. But this should be fine since the height is still relatively correct. Okay everybody, so this question we would like you to answer it in class. Question 3. Two students are discussing the work done on a system consisting of only the ball between the instant just before the spring begins accelerating the ball and the instant that the ball reaches the end of the ramp. The students make the following statements. Student 1. At first, the mechanical energy increases because the spring does positive work on the system. Then, the mechanical energy of the system increases again as the ball travels up the ramp because the ball's potential energy increases. Student 2. The mechanical energy of the system remains constant while the spring pushes the ball because the work done on the ball by the spring cancels the work done by the spring on the ball. Then when the ball is on the ramp, the mechanical energy of the system decreases because the ball slows down. Which of their statements are correct and which of them are wrong? Okay guys, so you can pause the video right here. So here are the answers for question 3, and as you can see, student 1 is correct for the first statement, whereas his second statement is wrong. And for student 2, all of his statements are wrong. That's about it. See you.